last lecture we derived formulas, several important formulas: lens maker's formula, lens formula, magnification, velocity of image. So almost everything that we need to solve problems, okay, of lenses. We derived everything. We discussed all the important concepts. Okay, let's solve these problems. Okay, from these problems we are going to learn a lot of more things. Okay, let's do it. The first one is the calculation of focal length. Okay, so we have this lens maker's formula. We use lens maker's formula to calculate focal length of any lens. Different lenses are given and all the required parameters are also given. Okay, it's like this. Or what I should do is, okay, that's fine. So this is my lens. The radius of both surfaces are given in all the cases, and the refractive index of the lens and surrounding medium in all the cases it is given. Okay, in each case we have to find focal length. Okay, so we are going to use this general formula: 1 over f is equal to mu relative minus 1 and then 1 over r1 minus 1 over r2. Okay, mu relative is mu of lens over mu of surrounding medium. Okay, surrounding medium. We are going to discover very important properties here. Let's start with the first case. The first case. Okay, assuming that in all of the cases, you see the quantities R1 and R2, focal length. Okay, they can be positive or negative. You see, otherwise radius is a positive thing. Radius of a circle is always positive. Radius of a sphere is always positive. But when we are using sign convention in terms of optics, okay, then we have to use sign convention. So I have to keep these values R1 and R2 with proper sign. Proper sign. The same sign convention we are going to use. We do not have any other sign convention. Same sign convention. Okay. So this is in all the cases we are assuming that light is coming from this direction. This is the incident light. In all of the cases. In all the cases. And it does not make any difference. You can do it from this side also. Okay. So whichever surface the light hits first becomes my first surface. Understand this? Okay. So if I assume that light is coming from this direction, so this surface becomes first surface. So it will be R1. The radius of this surface will be R1. The other will be R2. If I assume that light is coming from this direction, then this will become my first surface. Radius of this will become R1. The other becomes R2. Okay. So just to simplify things so that we can compare easily. And anyway, it is not going to make any difference. You will find out. Okay. You can do it yourself. So in all the cases, light is coming from the left. Okay. So first case, 1 over f1. Okay. First case is equal to mu relative. What is mu relative? Lens, mu of lens 1.2 over 1 minus 1. Okay. And R1, this is first surface. This is first surface. R1. Okay, its center is going to be on the other side. This is center of the first. This is center of the first surface. Okay, so R1 is to the right. Incident ray is towards right. R1 is to the right. For this, for all of these cases, this is going to be my sign convention. This is positive. This is negative. In all the cases, because in all the cases we are taking that incident light is going towards right. In all the cases. Okay, so distances to the right of lens becomes positive, to the left becomes negative. So this is the first surface, this is center of the first surface. So radius of first surface will be positive. Okay, it will be 1 over plus 20 minus 1 over R2. Okay, this is the second surface. This is second surface. Okay, its radius, its center is going to be somewhere here, C2. So its radius is to the left of this lens. So I will write minus 20 here. It is equal to, this is 0.2 0.2 times 1 over 20 plus 1 over 20. So 1 over 10, it becomes 1 over 10. 1 over 10. Okay. So this F1 is equal to plus, okay. So this is 2 over 100 plus 50 centimeter. Plus 50 centimeter. What is this? This is focal length of the first lens. Now what it means? I am getting a positive answer. Positive answer. That means this light ray, the light ray which is coming from left, for this light ray, okay, all of the light rays is going to converge at what distance? Plus 50. That means on the other side. Plus is this. That means on the other side. Okay. This other side here. Now, what type of lens is this? In terms of geometry, it is convex lens. In terms of the optical behavior, optical property, it is a converging lens. It is a converging lens. Okay. So, focal length of a converging lens is positive. You have to remember this. Focal length of a converging lens is positive. Now, second case. 1 over f2 is 1.2 over 1 minus 1 into. Now, this is the first surface. Its center is somewhere here. First surface. It is going to be negative. Okay, R1 is negative. 1 over minus 20. Minus 1 over. Second surface. This is the second surface. The radius of this surface is going to be to the right. Center of this surface is to the right. So this distance becomes positive. Positive. Okay, from the sign convention. So this becomes plus 20. Plus 20. Okay. This is going to be equal to 0.2 times. This is minus 1 over 10. This is minus 1 over 50. Okay. So what is F2? F2 is minus 50 centimeter. Okay, that means I have this incident light. Okay. Incident light after passing through lens. They are going to converge here, minus 50. Okay. Now, how can they converge here? Okay, this is a lens, this is a transparent medium. The light ray has to go to the other side. It cannot come back. That means actually it is diverging from this point. It appears to be coming from this point here. So this becomes a diverging lens. Okay, this distance is going to be 50 centimeter. This is 50 centimeter. Okay, it is a diverging lens. The focal length of a diverging lens is negative. Okay, and now the really interesting one. Okay, let's write the focal length. What was the focal length here? F1. Okay, what is F1? F1 is plus 50 centimeter. Okay, let me write it this way here. Okay, this is F1. F1 is plus 50. What is F2? F2 is minus 50 centimeter. Okay, let's look at the third case, F3. Radius remains the same. Refractive index of the lens also remains the same. What is the difference between first and third? This surrounding medium. Here it is air, mu is equal to 1. Here it is some other medium, 1.5. Okay, let's see what is going to be the difference. So this becomes 1.5. 1.5. Okay, now what it is going to be equal to? It is going to be equal to 1.2 minus 1.5. So minus of 0.3 over this is 1.5. What do you think? Okay, what do you think? Compare first and third. First and third. The only difference is in surrounding medium. In first case, surrounding medium is air. In the second case, surrounding medium is another liquid, another medium. Okay, it is 1.5. It is 1.5. Okay. mu relative, mu of lens and mu of surrounding medium, 1.2 over 1.5. Now this becomes a negative value. Okay, this becomes negative. Okay, so this is a minus of 0.3 over this. So so this becomes 5, 1 over 50. Okay, minus 1 over 50. This becomes negative. Okay, the lens remains the same. Lens remains the same. Okay, lens remains the same. It is a convex lens. It is a convex lens. It is the same lens. Everything is same. The only change that we made is we changed this surrounding medium. Earlier, the surrounding medium was 1. This was rarer. This is the medium of lens, 1.2. Surrounding medium is rarer. Here the surrounding medium is denser than the lens. What we see, focal length changes. Focal length changes, the behavior changes. Now it becomes negative, that means it becomes a diverging lens. This becomes a diverging lens. It is a convex lens, but it is diverging. It is a convex lens, but it becomes diverging. Okay, let's look at the fourth case here. Fourth case, this becomes 1.5. Everything remains same, only this thing is going to change. Now this will become minus of 0.3 over 1.5. Okay, this becomes plus 1 over 50. This becomes plus. Focal length is positive. It becomes that means light rays are going to meet at a distance of 50 centimeters to the right. It is positive. It is positive. Okay, so light rays are going to meet like this. Okay, now this distance is going to be 50 centimeters. 50 centimeters. What is this? It becomes converging. It remains the same lens, but now the same lens, concave lens, which was diverging here, it becomes converging in this medium. So the nature of lens changes. Converging becomes diverging, diverging becomes converging. When the surrounding medium is changed, and then there is a special condition. Okay, note down this thing. Note down this. Okay, when lens is surrounded by a denser medium. Okay, its nature changes. Okay, nature changes. Okay, converging becomes diverging. Converging becomes diverging. Okay, and vice versa. Okay, very interesting. Okay, if I have this convex lens in air, convex lens in air is a converging lens. Now the same convex lens, if I keep it inside water, let's say that this mu is 1.2. Okay, I keep it in water. Mu is 4 by 3. Okay, it becomes 1.33. 4 by 3. Okay, then the same convex lens. Okay, the same convex lens which was converging in air, it becomes diverging. Same convex lens becomes divergent. Nature changes. Focal length, what about focal length? The focal length will depend on this medium, of course. So we cannot say what will be the focal length. Focal length will depend on this. Okay, it will depend on this surrounding medium. Okay, the magnitude of focal length can become more or less depending on this surrounding medium. Okay, and then okay, what will happen if let's say this. What about this? Okay, what if mu of lens is equal to mu of surrounding medium? That means let's say that this is some oil this is some oil, its mu is also 1.2. then what will happen? This becomes 0. Okay, then F becomes infinite. That means you see, that means it becomes same medium. Light undergoes refraction only if there is change in medium. Now if this is 1.2, this also is 1.2, there is no change in medium, okay, the light will pass undeviated. There is no change in medium, okay, so this lens becomes, it's like, there is no effect of this lens, because for light there is no change in medium. Both mediums are same, here as well as here. Light will pass undeviated. Okay, understand this? Now let's look at the next ones. Flat surface. What is radius of curvature, radius of the flat surface? Okay, for a flat surface. What do you think? This fifth case here, 1 over f5 is equal to mu relative, 1.2 over 1 minus 1, like this. Okay. And then here I have R1. Okay, this is my lens R1. This is first medium, first surface. R1 is to the left of it, so negative. Okay, so 1 over minus 20 minus 1 over infinite. Okay, that's it. This is 0.2 times minus 1 over 20. Okay, so f5 is minus 100 centimeter. It is a diverging lens. Diverging lens, okay? So that means when light passes through this, it is going to be diverged. Okay. It is going to diverge like this. Okay, this distance is going to be 100 centimeter. Okay. Now what about this? This will be converging or diverging? Concave surface, convex surface. This lens is going to be converging or diverging? What do you think? Converging or diverging? Sixth case. Okay, let's look at this. So this is a 1 over f6. This is 1.2 over 1.5 minus 1. Okay. Center of both surfaces. Center of both surfaces. This is C1 and this is C2. Are on the same side. Light is going towards right. Okay. So this becomes positive and this becomes negative. So both are negative. Okay. So 1 over minus 30 minus 1 over minus 20. Both are negative, 30 centimeter, 20 centimeters. Let's see. This is going to be equal to minus of 0.3 over 1.5 times. This becomes 1 over 20 minus 1 over 30. 1 over 20 becomes positive minus 1 over 30. So this is like 60 here, 3 minus 2, 1 over 60. Okay. So this is minus of 1 over 5 times 1 over 60. Okay, f6 is minus 300 centimeter. This is a diverging lens. Diverging lens. Diverging lens. Okay, you understand? Diverging lens. Now what will happen if I keep the same thing in air? Okay, same lens, now I am keeping in air. What do you think? What will be nature? What will be nature? Converging or diverging? It is going to become converging, because this thing here it was negative. Now the same thing will become positive. It will become positive. What will be focal length? Focal length will be plus 300 or different. We cannot say. We have to calculate. Okay. So then this becomes over 1 here, over 1. Okay. So this becomes plus 0.2. Okay, this is plus 0.2 into this. Okay, so plus 0.2 times 60. 1 over 60. Okay, so this becomes this becomes what? This becomes plus 300. Plus 300 centimeter. Okay, again you see this is just a coincidence. Do not conclude anything from here. Okay, I am reminding you again. Do not conclude anything from here. Do not think that in air focal length is plus 300, so in any medium it will become minus 300. Okay. That is just because of this value. Mu was 1.2 here, mu was 1.5 here. If I change this, if I make it 1.8, if I make it 1.8, things are going to change. So do not conclude anything from this. No. Earlier the answer was minus 300, now it becomes plus 300. It is just because of these two particular values. Because of these two particular values. Okay, it is simply because of this. 1.2 over 1 minus 1. This becomes plus 0.2. And 1.2 over 1.5 minus 1. This becomes minus of 0.3 over 1.5. This becomes minus 0.2. The magnitude remains the same. That's why here also the magnitude remains the same, only the sign is changing. But that has to do only because of this particular combination. This is not a general property. Okay, keep this thing in mind. Okay, now, next one. You will see that next one here. Next one, what it is? I have a lens. Its focal length is 20 centimeters in air. Now, what type of lens it is, I do not know whether it is equiconvex, convex, concave, okay, plano-convex, or whatever it is, okay. It simply says that its focal length is 20 centimeters. So we will assume it to be positive. Nothing else is specified. I will assume it to be positive. Plus 20 centimeters. I am assuming it. Okay. I will write like this. 1 over f is equal to mu relative minus 1 over r1 minus 1 over r2. Okay. In air 1 over fa is 1.2 over 1 minus 1. Okay. 1 over r1 minus 1 over r2. R1, R2 are not given. They are not given. In water, I will write 1 over F water is 1.2 over, this is 4 over 3 minus 1. What do you think? Okay? Into 1 over R1 minus 1 over R2. Okay? This is equal to plus 0.2 into some constant here. This whole thing, it is going to have some value depending on R1 and R2, and depending on the nature of the geometrical nature of the lens, whether it is convex, concave, plano-convex, plano-concave, concavo-convex, whatever. But whatever is the geometrical property, it is going to remain same in the water also. If I have a sphere, its radius is 10 centimeter. Inside water also its radius will remain same, 10 centimeter. So this term is going to be constant inside water and in air both. What about this? This becomes 1.2 times 3 over 4. So this is 0.3. So 0.9 minus 1 minus 0.1 minus 0.1 times k, some constant, the same constant here. Now if I divide both, what do I get? F water over F air is plus 0.2 over minus 0.1. That means F water is minus 2 times F air. Okay. It reverses. So if focal length in air is positive, plus 20, in water it becomes minus 40. It's not becoming minus 20, it becomes minus 40. If focal length in air is minus 20, it becomes plus 40. Okay, do you see? You understand this? Okay, now the next problem. Okay, you should try to solve all the problems on your own. On your own. Okay. When a lens is immersed in water, its focal length remains same, but nature changes. Nature changes. That means converging becomes diverging, diverging becomes converging. That means the sign of focal length change. If focal length is positive in air, it becomes negative. The magnitude remains the same. Okay, I will write like this: 1 over f naught in air. Okay, in air, it is equal to mu over 1 minus 1, 1 over r1 minus 1 over r2. Okay, makes sense? In water, its nature changes. Now it becomes minus f. Whatever is f naught, if it is positive, then this thing becomes negative. If f naught is negative, this becomes positive. Nature changes. Okay, sign changing. This is mu over 4 over 3 minus 1. Okay, times 1 over r1 minus 1 over r. That's it. That's it. Okay. What is mu of length? I have to find this mu. So now can you find it? Of course you can find it. Divide it. Minus 1 is equal to this becomes mu minus 1 over this becomes 3 mu over 4 minus 1. 3 mu over 4 minus 1. Okay. So now you have this answer. 3 mu. Okay. So this becomes mu minus 1. Mu minus 1 is equal to minus of 3 mu over 4 plus 1. Okay. So bring it here on the same side. 4 and 3 7. 7 mu over 4 is equal to 2. This goes to the other side. Okay. That means mu is 8 over 7. Okay. 8 over 7. This is focal length of the lens. Okay, now the next one, interesting. What do you think? Okay, I have this lens here. It is R1 and R2. Now if I cut it into this half, okay, this becomes my lens. R1 and R2 remains same. R1 and R2 remains same. Okay, that means focal length is going to be same. Okay, that means if focal length here is f naught, this also is f naught. Focal length remains the same. Now what will happen if I cut it like this? If I am cutting it like this, okay, in that case I get this thing. Okay, plus this is R1, this is R2. This is R1, this becomes infinite, this becomes infinite, this becomes R2. Now it is going to change. It will depend on R1 and R2. It will depend on R1 and R2. So both parts are going to have different focal length, and different from f naught also. If it is f naught here, then here I will have f1 and here I will have f2. f1 and f2 both are different from each other, plus they are different from f naught. In this case, okay. But in one special case, we can find a concrete relationship. It's like this. If I take that both have same radius, in that case I can find a definite relationship. If I assume that both have same radius, and that is what we usually assume by default, if nothing else is specified. Okay? Okay, do you understand this? So that's what we are going to assume. Okay, so this is f naught here. Let's say that it is f, and this also is f. So both are identical, both are going to have same focus. Now this is 1 over f naught. 1 over f naught is equal to mu minus 1. Surrounding is air. Okay. 1 over r minus 1 over minus r. Okay. This becomes 2 times of mu minus 1, or let me write it like this, mu minus 1 times 2 over r. It is f naught here. Okay. Now what is 1 over f? Mu minus 1 remains the same. Now 1 over r minus 1 over infinity. Okay. It is going to be equal to mu minus 1 times 1 over r. Okay. Now we know the relation. We know the relation. Okay. It is going to be equal to f naught over 2. No, not like this. Not like this. This will be equal to half times of 1 over f naught. You see, this whole thing is 1 over f naught. This whole thing, okay. So this I can rearrange, half times this, so half times of 1 over f naught. I know the answer. This f is 2 f naught. Focal length becomes double. Okay, focal length becomes double. Okay, you have to understand this. Remember this. In case of equiconvex, this is equiconvex lens. Equiconvex lens. Only then if I cut it, I will get 2 equal halves. Okay, 2 halves, 2 identical halves. So both half is going to have double focal length. It is f naught here, it is 2 f naught here. Okay, this is about the use of lens maker's formula. Lens maker's formula. Okay, now let's do some problems based on lens formula. Okay, lens formula. Okay. Okay, first question. This is my lens, okay? This is focal length. And one other thing. Okay, for mirror, focal length is equal to r by 2. For lens, focal length is equal to 1 over focal length is mu minus 1 over r1 minus 1 over r2. Okay, do not write focal length is equal to r. Okay, there is no definite relationship or r by 2. This is only for mirror. It is not for lens. Understand this, not for lens. In some special cases, it may become r by 2, but that will depend on the refractive indexes. In general, this is not correct. This is correct only for mirrors, not for lenses. Okay. Note down this point also. Okay, so this f is, let's say, 20 centimeter, and I have an object. Okay, okay, at some distance d. Okay. What is value of f? What is value of d to get an image? Okay, first of double size, second at same distance, on other side. Okay, let's solve these two problems. Okay, you must have done such problems earlier also. We are just going to kind of rephrase it. Okay, and we already have done such problems. We have dedicated much time in mirrors. The similar concepts we are going to apply here also. Okay. Now, second, this f is 50 centimeter. Okay, I have a point object here. It is moving with let's say 10 centimeter per second, and this is 2 meter. What is velocity of image? What is velocity of image? Okay, let's find out. Okay, first one, understand this. Okay, nothing else is specified. What type of lens this is? It is a convex lens. It is a convex lens. This is a concave lens by its geometry. So if a lens is kept in air, this is air. In that case, a convex lens is converging lens. A concave lens is diverging lens in air, in vacuum. Okay, always. But if I change the surrounding medium, then the nature may change, okay, depending on the refractive index of surrounding medium. If surrounding medium is denser than lens, nature is going to reverse. Convex becomes diverging, concave becomes converging. Either case, focal length of a converging lens is always positive. Focal length of a converging is always positive. Whether it is convex or concave, try to differentiate these terms. Focal length of a converging lens is always positive. It does not matter whether it is a convex lens or concave lens. Convex and concave are geometrical nature, shape. Converging, diverging, optical nature. Okay? And focal length of a diverging lens is negative. In air or vacuum, in air or vacuum, convex is converging and concave is diverging. So here this is a converging lens, focal length will be positive. Here it is diverging lens, focal length will be negative. Now, first problem, okay, double size, image of double size. This is the only information that is given. Now that image can be real or it can be virtual also. Okay. If it is a real image, then what is magnification? It is going to be -2 because real image is inverted. Real image is inverted. It is -2. Okay, you understand this? What is magnification? In case of lenses, it is V by U. So V over U is -2. Okay. So V is going to be -2U. Now let's make use of the lens formula. 1 over F. Okay. So this is -1 over 2U minus 1 over U is equal to 1 over plus 20. Focal length is 20 centimeter. It's a convex lens in air becomes converging. Converging is positive. Okay. Now, if it is a virtual image, then this becomes +2. Virtual image is erect. Real image is inverted. That's why I am writing minus here and plus here. Okay. Then V over U it becomes +2. V is +2. Okay. +2U. Again, the mirror lens formula. 1 over F. Okay. So 1 over 2U plus 2U minus 1 over U is equal to 1 over minus, not minus, but yes, plus 20. Oh, it is the same lens, same problem we are doing. Okay. Understood? Now, this is a -3 over 2U is 1 over 20. Okay, U is -30 centimeter. -30. Okay, this is 2 over 2U minus 1 over 2U is equal to 1 over 20. U is -10 centimeter. minus 10 centimeter. Okay, and let's do the third part also. Virtual event is event. Okay, then we will combine all of that and we will derive some very important properties. Very, very important. Okay. Okay, same distance on other side, same distance on other side. Okay, I have this lens, this is my object here, this is my image here. This distance is D and this is D. Same distance on the other side. On other side. Very interesting, okay? 1 over V minus 1 over U is 1 over F. Okay? Now, this is my sign convention, positive and negative. So 1 over plus D minus 1 over minus D is equal to 1 over F. Okay? This is 2 over D is equal to 1 over F. Okay? What is D? This D is distance. I'm writing I'm writing the sign here when I'm writing U and V. But otherwise, this is a distance. It is always going to be positive. Okay? So this distance it becomes 40 centimeter. Very interesting. Okay? Many important properties we are going to summarize using these results. It's like this. The very first result. The second case we will discuss first. What is this distance? It is 2F. 2F. Okay. In case of this lens here, convex lens, it's a converging lens. This is my focal length F0. This is focus here, F, and this is 2F here. 2F. On the other side also, I will have these 2 points, F and 2F. We are not differentiating between first focus and second focus. Okay, understand it. Why? Because medium on either side of lens is same. If medium on either side of the lens is same, then both focal lengths are same. F1 and F2 are same. Okay? The only difference will be in the ray diagram. Now, in this case, what will be magnification? Magnification is equal to V over U. It is plus D over minus D, which is minus 1. Magnification is minus 1. That means if I have an object which is kept at 2F, the object at 2F, double the distance of focal length, 2F, I am going to get an image at 2F, and it is going to be of same size but inverted. Since we are getting the image on the other side, it is a real image. We have discussed this point earlier also when we were doing refraction from the curved surface. In case of refraction, light has to go to the other side. Light is transmitted. So real image is formed on the other side. Object and image will be on the either side. Okay. So that's how I am going to get my image. This will be the ray diagram. Okay. This is the ray diagram. A real inverted image. So object at 2F, image at 2F on the other side. Same size, inverted. You have to remember this. Remember this thing, okay? Now, double side. What is the object here? What are the distances? What are the distances? This distance is 20 centimeter. This also is 20 centimeter. This whole thing is 40 centimeter. This here is also 40 centimeter. This is U. What is V? What is V? V is minus 2u. It is plus 60 centimeter. Plus 60. What is magnification? Is minus 2. We started with this thing. Okay. U is minus 10. What is V? V is plus 2u. It is minus plus 2u. U is minus 10. V is minus 20 centimeter. What is magnification? It is plus 2. Okay. Let's draw the FBD. Let's draw the FBD. Okay, of course. The ray diagram is equivalent to FBD in mechanics. Okay, so I don't know how I uttered these terms. FBD. FBD is for mechanics, Newton's law. Anyway, ray diagrams in optics is equivalent to FBD in Newton's law in mechanics. Okay, interesting. Interesting things happen. Okay, so this is, let's draw the FBD of this situation here. Same lens. I have this same lens here. Where is the object? At a distance of minus 30 centimeter. This is my focus F. This is 2F. The object is here. This distance is 30 centimeter. Object is between F and 2F. In case of mirrors, this point is known as center of curvature. Here I am not calling center because center is here. And anyway, I have two surfaces, both surfaces have different center. So which center? So no center. There is no center. Okay? We have optical center here. This is optical center here. Okay? Now the object is between F and 2F. Where is the image? Plus 60. It is here on the other side. This is my F here. This is my 2F here. And the image is somewhere here. This is my image. This is the object here. Okay. Image at this distance. This distance is 60 centimeter. Object between F and 2F. Compare this with a concave mirror. Convex lens behaves like a concave mirror in terms of the properties of its image. Okay. Magnification is minus 2. That means I am going to get this inverted image. And real. Okay. Double size inverted on the other side. That means it is real image. Inverted, that's why also it is real. I can draw the ray diagram like this. Okay, and then I can do it like this. I need two light rays. That's how they are going to create image. This is something you have to remember. Object at 2F, image at 2F. Object between F and 2F, image between beyond 2F. It's like the same thing that happens in case of concave mirror. Object between F, focus and center, image is beyond center. Okay, object at center, image at center. Here also, object at 2F, image at 2F on the other side. Now, reciprocity. Interesting thing, reciprocity. Okay, what will happen if I keep an image, if I keep an object is between F and 2F, image beyond 2F. Now I can interchange. I can keep my object here. Object is beyond 2F, then this becomes image between F and 2F. Okay, I can simply interchange it. It's like this. Okay, so this is 2F and this is F, this is F. Here also it is F here and this is 2F here. Okay, it's like this. Fine, so F and this is 2F. That's okay. Now, here is my object. I should get my image between F and 2F. Simply because of reciprocity, I can answer this. Okay. Let's see how the FBD looks like. Okay, the ray diagram looks like this. Looks like this here. Okay, and let's take one other light ray. I can take this one. Now this appears to intersect here. Okay, object beyond 2f, image between f and 2f, real image. And one more thing here, the image is magnified, enlarged. Here the image is going to be diminished. Things reverse. If it is enlarged here, it will be diminished here. Positions interchange. Positions interchange. This magnification thing reverses. If it is magnified here, it is diminished here. Okay, now, one last thing, okay. Object at infinity we already discussed. It is going to be at focus, standard thing. Okay, don't need to be repeated. Now, so I keep my object here beyond 2f. I keep my object at 2f, between f and 2f, at focus, infinity. Now, one last position, that is between lens and focus. Okay, let's do this. It corresponds to this problem here. Okay. Now the image is on the same side. If you know only this, from this also you can conclude that it is going to be a virtual image. It is a case of refraction. Light is going on the other side. In case of refraction, light comes back on the same side. This is a case of refraction. Light should go on the other side. Then if I am getting a real image, it must be on the other side, not on the same side. I am getting an image on the same side. That means light rays are not actually meeting. They just appear to be meeting. That means this is a virtual image. Okay. I can also conclude it from this magnification. It's positive. That means image is erect. It must be virtual. Okay. Let's see how the ray diagram, how this FBD thing is going to look like. Okay. Let's understand it this way. Okay, this is F and this is 2F here. F and 2F here. On the other side also at same distances I have these 2 points, F and 2F. Okay, now object here between lens and focus. My object is somewhere here. Here is my object. I am getting my object here at focus. It's just a coincidence. I can get it anywhere. It just depends on this value. Because for this particular value, I am getting it at the focus. At focus means at the location of focus. Now, how the ray diagram is going to look like? Okay, if I consider this, it is going to pass like this here. Okay. Now let me take one other. These two are diverging light rays. They are never going to meet on the other side. But if I am looking from this side here, okay, I am looking from here, this is my object I want to look at, I am holding a lens. Okay, so I am receiving these two light rays. Okay, so it appears to me that these two light rays are coming from a point somewhere here. So this becomes my virtual object. Virtual, erect, magnified. Magnified means enlarged. Enlarge. I can enlarge this. This is the simple convex lens, converging lens. A small converging lens. My object, if I see it through the lens, it's magnified. Virtual image. I cannot get it on my screen. I can only see it. I can only see it. Okay. If I keep something here, I see nothing. I get nothing. Here, these are real images. So if I have a screen here, okay, I will see an image right here on the screen. It's a real image. It's a virtual. Now this thing is used actually for simple magnifier. Okay. Simple magnifier. Or simple microscope. Simple microscope. Okay. We are going to study these things in optical instruments, simple microscope, compound microscope, and all that. Okay. Remember this thing. Now one other thing, it's a convex converging lens. From converging lens I get all sorts of image. I get real, I get virtual, I get magnified, diminished, erect, inverted, all type. Okay. And now one other very interesting thing. The object is at infinity. Where am I going to get my image? Let's say that I have this object here, a very large object here. It is at infinity. Infinity. Okay. Then where do I get image? I get image at focus. Focus. Now if all the light rays are parallel, then it will be a point-like object, point-like image at focus. Okay. But if I have this extended object, a very large distance, in that case I get my image in focal plane. Focal plane. It will be at here at the same distance focus. Okay. So this is something that's how I am going to get my image. Something like this. These are the parallel light. They are arriving at from this large object at large distance. Okay. All of them are going to converge like this here. That's how I am going to get an image. A real inverted image in the focal plane at focus in the focal plane. Okay. So that happens when object is at very large distance. My focus is here. Now as the object approaches, at some time it is near to it, but beyond it. Okay. My image is here. So initially the image was here at focal plane. As the object is approaching, but understand this. When object is at a very large distance, image is here at focus. As the object approaches, this image is moving, the image is moving towards 2f. The image is moving towards 2f. Now when the object reaches 2f here, image is at 2f. Okay. So image starts moving from focus. It goes from focus, it goes to 2f. The object is here. Now when object keeps on moving, when the object is between f and 2f, okay, in that case this starts moving. It goes beyond 2f. Okay. Now when the object is here, this is my object, this is my image. Object and image. And this is my object. Okay. Now if object is here at a large distance, image is somewhere here. Okay. When object comes here, okay, the image goes beyond this. Okay. No. When the object is here, between f and 2f, the image is here. When the object reaches focus, it goes to the infinity. Okay. So sometimes this very interesting question is asked. Okay, it's like this. When object is at a very large distance, the image will be at focus. What is distance between object and its real image? Okay. What is minimum separation between an object and its real image from a converging lens of focal length f naught. What is minimum separation? When object at very large distance, image at focus. When object at focus, image at very large distance. When object at 2f, image at 2f. And that actually is the minimum possible distance between object and its real image. Okay, the answer, think about it, is going to be equal to 4f naught. This is 4f naught. This is my object, real image. Okay, This is 2f naught here and 2f naught here. Answer will be 4. Okay. So should we do this problem? Okay, let's complete this problem. Let's complete it. But before we move on to this problem, we just discussed. Remember this result, very important result. Think about it. Think about it. Very important result. Also remember, from a convex lens, I get also all the possible types of images. Real, virtual, erect, inverted, magnified, diminished. Okay. What about a concave, a diverging lens? It behaves like a convex mirror. Convex mirror is converging, convex mirror is diverging, concave lens is also diverging. Both are diverging. So from a diverging system, I get same type of image. Okay. So what is the nature of image from a diverging lens or diverging mirror? Okay. It's always of same type. Diverging lens, diverging lens or mirror. Okay. A concave lens becomes diverging. A convex mirror is diverging. Both are diverging. Nature of image is same for both. Okay. So no matter where the object is, no matter where the object is, okay, the image is always going to be of same type. This is my object. It is going to be diverged from here. And if I take any other light, now these are two refracted light. So when I look it from this side, from here I am looking, okay, I receive these two light rays. I think that these two light rays are coming from a point somewhere here. I see my object here, image here. Okay, there is no difference between object and image. You cannot differentiate object and image. Always, no matter where the object is, no matter where the object is, I am always going to get a virtual. This is a virtual, erect, and diminished image in all the cases. In all the cases. Okay. Let's complete this because I have written it, and then in the next class again we are going to continue with this. Okay. Okay, so here it is. I have to find what? Velocity of image. Velocity of image is v square over u square and velocity of object. Okay, it is going to be equal to m square and velocity of object. Now I need to find v and u. Okay, now 1 over v minus 1 over u is 1 over f. 1 over v is 1 over f plus 1 over u. 1 over f. What is f? 50 centimeter. It's a diverging lens. I will write minus. I will write minus 50 plus 1 over object 2 meter minus 200. I have this. So this becomes minus 1 over 50 minus 1 over 200. So this becomes 200 here. Minus 4 minus 1. So 5, 40, okay. So V is minus 40 centimeter. What is M? V over U. V over U, okay. So minus 40 over minus 200, it becomes 1 over 5. Okay, that's how we solve it. And then the velocity of image is equal to 1 over 5 square times 10 centimeter per second. 10 centimeter per second. So that's it. This is my answer. So 25. Okay. So this is 25. So 10 over 25 centimeter per second. This will become 4 millimeter per second. Okay. So that's about it. Start doing some problems from problem sheet. Next class we will continue with problems.